Welcome, everyone. My name is Brian Bailey. I am the session chair of this session. The session is titled Erosion Solutions. A couple of notes before we start the presentation. You'll have the opportunity to ask questions during this on-demand session by clicking the question button at the bottom of the video screen. Your question will be sent to the presenter to answer as soon as they are able. To claim PDH credits for this session or any other educational session, you simply need to click on the Claim Credit button on the conference homepage. From there, you will fill out a survey for the sessions that you attended. And please note, you will need to have the verification code shown in this session to verify that you attended and to ensure that you receive the proper credits. Please enjoy the presentations.
Hi, everyone. Thank you for your audience. Today, I'm going to present a case study of a project located on the Delaware Bay in New Jersey that used geotextile tubes to protect a historic lighthouse against erosion. Before jumping in the case study, I would like to make a quick overview for those who are not familiar with this technology. The geotextile tubes were first used in the Netherlands almost 60 years ago for marine applications. It basically consists of filling up a geotextile bag with slurred sand through filling ports. The liquids pass through the pores of the geotextile and the solids remain encapsulated within the tube. Using these monolithic elements, many marine structures can be created, such as breakwaters, dikes, jetties, sand dune cores, and man-made islands. In the early 90s, these containers were used for the first time for sludge dewatering, as you can see on the top right photo, using the same concept of separating the solids from the liquids. Over the years, this technology evolved in such a way that mega projects like the Amouage Islands in the Middle East could be executed, as you can see on the photo at the bottom right.
This slide shows another milestone. The first marine application in America was in 1993. 2 miles of geotextile tubes were installed to protect the shoreline of Atlantic City, New Jersey, not too far from the East Point Lighthouse, focus of my presentation. I visited the project in 2020 and couldn't be happier to see that the tubes are still there after 28 years. All right, let's focus on the case study. First, I'm going to present an overview of the project, and then I'm going to go deeper into the details. The challenge was to protect the historic lighthouse, which was critically endangered after years of erosion caused by storms and hurricanes. The proposed solution was to build a 600 feet long structure consisting of 8 sections, each section consisting of 3 elements. The first element installed was the scour apron, the second was the sand-filled mattress, and finally the geotextile tube unit. The final result was great. The installation of the system was fast in spite of being the contractor's first experience with the technology. The solution proved to be cost-effective, especially when compared to previous restoration works. It took over a month to finish the installation, and the erosion hasn't advanced since then. The project is located right by the mouth of the Maurice River that flows into the Delaware Bay in New Jersey. This region is highly affected by storms that enter the bay, causing serious erosion. The importance of this project is highly connected to the historical relevance of the building. The East Point Lighthouse was built in 1849, and it's the second oldest lighthouse in the state of New Jersey. In 1995, it was added to the National Register of Historic Places for its significance in engineering, maritime history, and transportation. Now the lighthouse building holds a small museum, and you can go upstairs like I did and appreciate the view where the lamp used to operate. It's important to highlight that erosion is also an environmental threat. The lighthouse is surrounded by wetlands, which is a preserved ecosystem that provides natural erosion protection, and it's home for many local species. It's shocking how much land has been lost over the last decades. This slide shows the progress of the erosive process over the years and how aggressive it's been. Okay, let's move on to the conceptual design. The little red square on top of the slide shows the relative position of the lighthouse to the structure. The wetlands are located on the right. The different colors show the different lengths that were used to allow us to accommodate the units and make the necessary curves. This is the sequence of execution of each section. The sections were installed from right to left. Regarding the geosynthetics, we used a high-strength woven geotextile to fabricate the tubes in the scour apron. For the sand-filled mattress, we used a geocomposite that can also fabricate the tubes if it's needed. This new composite provides the strength of a woven geotextile in combination to the durability, UV protection, and abrasion protection provided by the extra layers of fibers weaved together, as you can see on the right side of the screen. A software called Tenkata GeoTube Simulator was used to design the system. This slide shows the graphic output of it. Taking into consideration the circumference of the tube, its height, density of the material, type of fabric, type of seaming, and type of filling board, we can calculate the safety factors for the circumferential forces, longitudinal forces, and filling port stresses. From the GeoTube simulator, we determined the scour apron width that prevents the foundation of the tube to be scoured by the energy of the waves. It's recommended to keep a 2-to-1 ratio for the width and the height of the geotextile tube. Usually we don't use the sand-filled mattress on top of the scour apron, but in this case, the designer wanted to use the sand-filled mattress to provide extra weight to the scour apron. The final step was to cover with sand the entire structure. Here's an aerial shot of the job site and the first section being installed. At the top, you can see the red roof of the lighthouse and its relative position to the structure. Here's a photo of the site preparation. This slide shows the silt fence to protect the wetlands and also the pipe that was installed to release the water and help the crew during construction. A slurry box was used to feed the system and fill the tubes. They used the water from the bay and brought sand from a quarry nearby. No booster was necessary to fill the 600 feet long structure. This is a detail of the flat ends. They are recommended to help keeping the same height longitudinally, avoiding the V notches, and also for cost-saving reasons, since you don't need to overlap the units. This slide shows the scour apron being installed. Both scour apron and geotextile tube unit are delivered with instructions of how to be unfolded. This way, we make sure the product is installed correctly. Another photo of the scour apron being installed. And the sand-filled mattress being installed. We ended up recommending that the pieces were filled in a separate area and placed using an excavator. The process worked pretty well, and it was also faster. This slide shows the excavator placing the sand-filled mattress. All the sand-filled mattress pieces already in place. Now it's time to fill the anchor tubes. This slide shows the contractor installing a pipe to connect to the filling pipeline that brings the slurry from the sandbox. And here's the structure already covered with sand. I personally think this is a great photo to show the structure in action. This was the first storm after the job was concluded. The anchor tube did the job and anchored the scour apron into the sand, protecting the foundation of the structure. The sand color of the geotextile tubes worked really well. It blends in the landscape, causing less visual impact. As you can see on this photo, there's no rocks spread all over the place, which shows how nice it is for the beachgoers to enjoy the beach without the risk of hurting themselves. And we also see the horseshoe crabs that spawn on the beach of Delaware Bay every year. It's important to address that the geotextile tube is inert and interacts very well with vegetation and marine life. Thanks for your attention, and I also want to give special thanks to the Lighthouse Administration that provided information and photos that were used in my presentation. I'll be happy to answer any questions you may have. Have a great day.
Good day. My name is Tom Stevens. I'm with Tenkata Geosynthetics. First, I want to thank the IFAI and the IECA for selecting this paper for presentation at the conference. Also, I want to thank you for taking your time out of your day to listen to this presentation. I hope it's both informative and educational and maybe even entertaining. So with that, I'd like to start presenting creating a soft green living shoreline using sand-filled composite geotextile tubes and native species of vegetation.
What is a living shoreline? I want to read this to you because as you go through the presentation, I want you to notice how this project checks all the boxes of being a living shoreline. And this is the NOAA definition of a living shoreline. NOAA is the National Oceanographic and Atmospheric Agency. A living shoreline is a green infrastructure technique using native vegetation alone or in combination with low sills to stabilize the shoreline using natural alternatives to hard stabilization methods like riprap or bulkheads, and providing numerous benefits including nutrient pollution remediation, essential fish habitat structure, and buffeting of the shoreline from waves and storms.
A complimentary NOAA brochure, they describe the elements of living shorelines. And one of the elements of living shorelines is described as a geotextile material tube. And it talks about the dimension of those tubes, but also lists the specific benefit of this geotextile tube is that they provide shoreline protection to weaken the wave energy against erosion of the shoreline. Shoreline protection can be characterized in a color spectrum from green to gray, where living shoreline is in the green spectrum and hard armor protection such as riprap is in the gray area. And today we're going to be focusing on using vegetation and edging for low sill construction of a shoreline or a living shoreline. Project that we're going to focus on today is located in the Potomac River on the east coast of the United States. It opens up into the Chesapeake Bay And this is a very sensitive environmental location. Everybody knows about the Chesapeake Bay and the pollution that's occurred in this area, and also the erosion that's occurred on the shoreline, and a lot of the efforts that have been taken to try to prevent erosion, but yet try to have a green environmental solution to these erosion projects. And this is what we're going to focus on today. The project is known as Curiamon Bay.
The Curiamon Bay site is located just south of a barrier island right here in the Chesapeake Bay. And as you can see, that this barrier island has been breached. It was breached in the not too distant past by a hurricane, and it's caused severe erosion of the site.
The breach in this barrier island is indicated by this red oval. And as you can see, it's quite a large opening there and is opened up the area that we're going to talk about today to erosion, to coastal erosion. This boat launch is one area that's had a tremendous amount of erosion occur due to this break in the barrier island, because it's directly south of there, and it's taken a lot of the brunt of the storms through the years, and it is just breached this area, eroded it almost away, and that all of that sediment from that erosion has been deposited in the area around the boat launch and is completely unusable today.
And as you can see, this spit of land has almost totally been eroded away. This slide contains the plan view of the living shoreline that is designed by the engineering firm Apex in Richmond, Virginia. You'll note that there are two parallel rows of geotextile tubes that are to be installed to create this soft armor protection of what will become a wildlife habitat.
Also, the design incorporated the use of dredge material taken from around the boat launch in the channel leading away from the boat launch to be placed between the geotube structures, over which native grass would be sprigged to establish this native environment. The engineer chose a geotextile that was to be used to fabricate the geotube unit, which is a tri-composite geotextile. The center is of this geotextile is a high-strength woven polypropylene. The top layer is a quarter of an inch thick of very coarse denier fiber, which is very highly UV resistance, abrasion resistance, and impact resistance. And the bottom layer underneath is a layer of non-woven, which helps bind all of this together when the material is needled to create this tri-composite.
Contained in this slide is the table of properties for the tri-composite geotextile that was used to fabricate the geotube units for this project. This slide is of a freeze frame of a video of a hurricane impact test, an ASTM hurricane impact test. This test is conducted by firing a 5-pound 2x4 at a given construction material, in this case the geotextile that the geotextile tube is fabricated from. To pass the hurricane impact test, it has to withstand 3 direct impacts of this projectile fired at 100 kilometers per hour. This slide is just provides the details of this testing that occurred. Again, 3 impacts of 100 kilometers per hour, no surface damage or minimal, and no rupture of the fabric. This slide is an image of the rotating drum abrasion test where the geotextile used, this tri-composite geotextile used for this project, was subjected to 140,000 revolutions with a basalt gravel on the inside. 70,000 revolution one direction, 70,000 in the other direction, and it maintained 96% of its design tensile strength. Survivability of a geosynthetic on any type of project is very important when exposed to long-term exposure to UV. In this case, the geotube is going to be installed there on the coastline of Virginia, and it has a UV exposure of about 3.0 kilowatt hours per meter squared per day. Based on accelerated UV testing, this tri-composite geotextile has a survivability half-life of 50 plus years at this location. Construction on this project started in June of 2020. The contractor used the mechanical dredging to a hopper to fill the geotextile tube units. To aid in the distribution of the fill material, the contractor used 2 water pumps to slurry the material in the hopper and aid in the distribution throughout the length of the tube. The photo in this slide was taken the next morning after the filling of the first geotube units. As you can see, there's the native species there of crab and jellyfish are abundant in the area and undisturbed by the construction. This photo was taken during the first week of construction. As you can see there, as you look through the water, the sediment and sand that's already beginning to accumulate on the river side of the geotube structure. This image is a vivid demonstration of how this geotextile tube structure will perform as to prevent erosion of the shoreline. It was taken at the completion of the installation of the 2 parallel rows of geotube structures are to protect this wildlife habitat. 2 parallel rows of geotextile tubes, and it also is a good image of what this low sill, soft armor looks like for a living shoreline structure. The installation of these structures, and you can see there that the marine growth is well established already. In a very close-up view of this 1/4 inch thick of fiber on the top of this surface has all been sedimented in due to the fact that there's been the sediment is accumulated and captured in this matrix during the rise and fall of the tide. What you see in this image, in this underwater image, is the marine vegetation that has taken hold and has been established on the surface of this tri-composite geotextile material. Varieties of native species of grass, marsh grass that were planted in this wetlands area. Again, there were 22,000 different sprigs that were planted of 7 different varieties of marsh grass. They would start on the outside of the wetlands area here, planting 1 species, and as they move to the middle, which is a little higher ground there, they'd plant a different species, very similar species, but the ones near the shoreline where it comes in contact with the salt marsh here, salt water here in the river, is acclimated to that type of environment. And as you come to the middle, it's the type grass that is a little bit a different grass, not subjected to saltwater intrusion. But again, 7 different species planted in rows to create this very natural habitat. This was very important for this project, so it checks all the boxes of a living shoreline, as we discussed earlier. It's a green shoreline. Geosynthetic materials now have the capability of incorporating with native plants to create a living shoreline. Also, the geotextile tubes are capable of being sustainable over a long period of time in this type of marine environment. They're also a low-cost solution to traditional hard armor construction materials and methods. And finally, this type of construction doesn't have any adverse effect to the natural environment. A very successful project. Any questions that you may have, please feel free to contact either me or Joe Little. Below is our email addresses, and feel free to contact us if you have any more questions about this project or how this technology could be adapted to one of your projects, please do not hesitate to give us a call. Again, thank you very much for listening and taking time out of your very busy day. Goodbye.
Hello and welcome. My name is Brian Hamilton with Tenkata Geosynthetics. Today I'll be presenting engineered geotextile solutions for inland waterway erosion protection. Inland waterways are continually subjected to natural erosion, resulting in flow meandering, flooding, and damage to infrastructure. As a result, revetments are used to help mitigate and provide protection against bank erosion. Common systems used for construction of revetments include riprap, rock-filled gabions and mattresses, concrete blocks, concrete mattresses, and soft-covered geosystems, which is the subject of this presentation. Riprap is widely graded rock, usually 2 to 2.5 feet in size, and is placed in bulk to give an armor layer about 2 to 3 layers thick. Construction is fairly simple, uses standard equipment and a small workforce. Riprap can be costly if hauling over long distances and may not be available in some locations. Gabion mattress is typically a basket, steel wire basket that utilizes small rock as fill. Again, construction is simple, uses standard equipment and a small workforce. It can be costly if hauling over long distances because of the rock. It may not be available in some locations and could be an issue in saltwater environments due to corrosion and rust. Concrete blocks and slabs are typically precast concrete products of various designs, but also include cast-in-place reinforced concrete slab. Construction process is fairly simple, and standard on-site plant or equipment is typically suited for these type of systems, although heavy lifting equipment or machinery could be needed or required for lifting cable-linked blocks. These types of systems can also be costly if hauling over a long distance. Concrete mattresses are typically systems of 2 layers of fabric systematically linked or sewn together to create an internal space that's filled with concrete or marine grout, resulting in a hard, durable, and aesthetic surface finish. The construction process is simple, using basic equipment, but the system does require special detailing attention at the toe and at the crest and end terminations. Although rock and concrete-based systems are traditionally used to construct revetments, a soft and environmentally friendly solution, or geosystem, is becoming more commonplace. Examples of geosystems include geotextile bags, geotextile tubes, and sand-filled mattresses. Today we're discussing only geotextile bags and sand-filled mattress. There's a wide range of engineered geotextiles and composites used for fabricating geosystems. These engineered fabrics are designed for strength, robustness, abrasion resistance, and UV resistance. The versatility of these materials, together with their low cost and simple design, makes them a viable alternative to hardcover systems. Geotextile bags are basically containers that are filled with dry sand that have volumes between 1/2 cubic yard and 13 cubic yards. Anything smaller than 1/2 cubic yard is usually considered to be a sandbag. They're used in a variety of temporary and permanent structures, including revetments. These are 2 standard geometric designs for geotextile bag structures. Notice the effective thickness of the structural elements are dependent on the manner in which the units are installed. The figure on the left shows horizontal placement with 50% overlap between adjacent geotextile bags. And the figure on the right shows placement of abutting geotextile bags that follow the inclination of the slope. Of course, design rules and calculations are used to establish criterion such as stability on slopes, stability in waves, stability in different types of flow, stability when subjected to overtopping currents, shear of the subsoil, and liquefaction. We'll talk more about the design later in the presentation. Again, there are a variety of geotextiles available for making geotextile bags. The material choice is evaluated during the design cycle and is derived after considering aspects that contribute to potential failure modes and safety considerations, such as tensile strength, sand tightness, and permeability or permittivity. The last few photos we've seen are of a geotextile bag revetment and a riverine application to prevent bank erosion. The material is a multi-layered engineered composite geotextile known for its durability capabilities. It is designed to perform under long-term exposure to the open environment. These geotextile bags are made from a high-strength woven polypropylene geotextile, obviously beige in color. Note how they've been installed in both a submerged and emerged application. Also notice that the geotextile bags come in different shapes, sizes, and colors, offering design options to the engineer. This photo shows the choice to increase thickness of the revetment by installing the geotextile bags horizontally, but in a lengthwise fashion as opposed to sideways. Geotextile bags can be filled in a few different ways. They can be filled mechanically, hydraulically, or by hand. The placement of geotextile bags can be done using a crane with a lifting strap or harnesses on land or in water. Dumping of geotextile bags has also been done using dump trucks. The geotextile bags shown here were lifted into place with straps and seated by applying pressure from the excavator bucket. There are a number of ways to rig harnesses for lifting geotextile bags. Here they're using a rope system to lift sand-colored composite geotextile bags into position. This photo shows a high-strength woven polypropylene geotextile bag being hoisted using more elaborate rigging. The geotextile bag is being placed into a dump trailer where it was transported to the revetment and dumped into place. These are the largest geotextile bags known to have been deployed. They are 65 cubic yard units that were filled at the terminal at the Panama Canal, placed on a barge, and then hoisted using a geogrid harness. The geotextile bags were lowered onto the canal floor to create a cofferdam so that concrete could be pumped behind them to fill in scour holes beneath the pier. These photos are from a Missouri DOT project on the Mississippi River. Open-top geotextile bags were placed in custom-made bins, filled with number 57 stone, sewn shut, and then hoisted using nylon strapping. They were lowered 85 feet into the river and positioned using side-scan sonar as scour protection around the bridge piers. You can imagine the design consideration for material in this application, especially tensile strength, lifting heavy stone with straps biting into the geotextile under the immense weight. One of the advantages to the green-colored composite geotextile is that it can be used as a green solution, not only due to its color, but also because it traps entrained sediments and promotes rapid vegetation growth. Here we see, or don't see, geotextile bags completely covered in vegetation. This figure shows a typical geotextile bag revetment, like the last photo we saw, with a filter fabric on the bank as added protection against subsoil erosion and vegetation on the face of the structure. You can get very creative using geotextile bag structures for embankment protection. This design uses them in a submerged application to fill a scour hole. Sandfield mattress is a double fabric layer product. The top layer is an engineered composite fabric that provides excellent abrasion resistance and durability and is capable of trapping settling sediments and particles. The internal space created between the two fabric layers is filled with sand to form a robust and flexible sand-filled mattress. The range of products for sand-filled mattress includes green and beige color. Green color is typically used in areas where vegetation establishes quickly, whereas beige color is used in areas where vegetation does not establish easily, usually at the water level or in the water. The green and beige colored geocomposite is pictured here. Again, green is mostly used above the high water line where vegetation is present, and sand color is mostly used to blend in where there is no vegetation and where it comes into contact with water. But they're both the same material and both can be used in either scenario. Sandfield mattress has several advantages. It's very cost effective, can be used as a green solution, requires little equipment, and is a very simple installation process. Does not require any heavy machinery. It's flexible and conforms to curves, and it bends easily, and it can be installed in the water if required. Sandfield mattress can be used in a number of different applications. It could be used as a channel liner. It could be used for riverbank protection. Sandfield mattress can be used for protection banks on levees. Notice in this scenario how they use geotextile bags as a toe or edge protection, protecting the mattress from scour. It could be used for lakeshore protection. And Sandfield mattress can also be used for bridge abutment protection. Sandfield mattress is usually supplied in a 12.5 foot by 85 foot long roll. Each roll has 10 tubular compartments or tubes that run the length of the roll that have a 2.3 foot circumference that can be filled to an effective thickness of 9 inches. Once filled, the Sandfield mattress decreases in the direction perpendicular to the tube to 10 feet. In other words, it draws in to have a 10-foot wide filled width. This figure shows a typical revetment design cross-section. Like any other system, a detailed design is carried out for Sandfield mattress structures. The structure is assessed in respect to the stages shown in the design procedure, including setting crest and toe levels, stability requirements for wave and water flows, and calculating slope, etc. In most cases, the design calculations used for geosystems are the same as those used in the design methodology for hardcover systems, such as place block revetments. This is the stability criterion of Sandfield mattress under longitudinal flow attack. This design chart shows an example using turbulence, critical flow velocity, and water depth factors to help determine the extent of turbulence in the water flow. This is the ratio used for determining stability of Sandfield mattress in waves. It includes the factors for wave height, relative density of the Sandfield mattress, effective thickness of the Sandfield mattress, slope, and the breaker parameter, which is the ratio between the slope angle and the wave steepness. It should be pointed out that Sandfield mattress is not suitable for strong waves, generally anything over 3 feet high. This is the recommended design retention criteria for Sandfield mattress. A geometrically closed geotextile is used to manufacture Sandfield mattress. That means the pores are so small that the sand is physically blocked, so it will prevent erosion for all hydraulic gradients. Sandfield mattress should be evaluated for geotechnical stability. In addition to the design parameters we have already discussed, certain aspects during construction also require attention, such as filling to maximum density, maximum contact with the slope surface, limiting stretching and pulling to restrict tensile loads, overlapping of adjacent panels, and proper anchoring and end terminations are also very important. Sandfield mattress must be anchored in a trench at the crest above the waterline. Different details can be used for edge protection on Sandfield mattress, including anchor trenches, concrete toe berms, riprap, and geotextile bags. In addition to the crest and toe anchor detailing, appropriate termination details should be adopted at the ends of Sandfield mattress structures as well. These methods may be similar to those used at the crest and toe, but tend to be very site-specific. These are the mechanical properties and quality assurance that you would find on a technical data sheet for Sandfield mattress. The specification for Sandfield is based on the criteria we saw earlier depending on a stationary or dynamic hydraulic load. Of course, to reach maximum density, the sand should be free of any material susceptible to volume change, including marine mud, swelling clays, and collapsible soils, as well as materials containing any vegetation, wood, toxic materials, metal, etc. Typically, medium grain size sand with a D50 value that falls between 0.2 millimeters and 0.6 millimeters on the particle size distribution curve is specified for sand-filled mattress. This figure shows the anatomy of a sand-filled mattress installation. We're going to discuss installation in the following slides, but a few notables here include the anchor trench and end terminations we discussed earlier in design. Also, depending on the edge treatment, sand-filled mattress may be filled across the toe first before filling the entire panel. And panel overlaps, or closed edges, are installed in the upstream direction. As part of the installation, some pre-planning is usually necessary. This may include estimation of panel sizes, as well as cutting and joining adjacent panels of sand-filled mattress. Also, slope preparation, trenching, and other profiling may be needed before the sand-filled mattress is laid out according to the engineer's instructions. Several workers can easily place sand-filled mattress on a prepared slope. Notice the overlapping of panels. This is one way to connect adjacent panels and is usually performed when installing one panel at a time. As we discussed earlier, sand-filled mattress can also be adjoined by lacing, sewing, or using a pneumatic stapler with hog rings. These methods are usually incorporated when placing multiple panels of sand-filled mattress at one time. It may also be necessary at times to join panels of sand-filled mattress in the machine direction or lengthwise. This can be done by removing seams from the ends of each panel, sewing the bottom layers together, and overlapping the top layer and resewing them as well. This can be executed in the field using handheld sewing equipment. Once the sand-filled mattress has been placed, the internal space, or tubular compartments, can be filled with sand. This is accomplished using a small hopper to mix a sand slurry that is carried the length of the tube by gravity. Also, a hay pick can be used to lift the top layer of the mattress to allow easy flow of sand down the length of the tube. Here we see the advantage of sand-filled mattress being flexible and conforming to curves. Also, graduated links of sand-filled mattress can be installed to cover slanting edges and sharp angles. This is another view of a sand-filled mattress structure on a canal bank. Notice the trench at the crest has been backfilled to anchor the mattress. Just like geotextile bags, green composite sand-filled mattress easily blends in with the environment and can promote the rapid growth of vegetation. Thank you again for taking the time to attend this presentation. If you have any questions or would like more information, please feel free to contact me and I'll be glad to help.